So your server is holding a whole pile of requests at once, and every one of them is at a different point in its life. One is halfway through a 2,000-word answer. One arrived a second ago and nobody has read it yet. And one is about to say its very last word and go. So on the next step, which of them gets served? And how often does your server get to change its mind about that? So we're going after that second one today because it turns out to be the whole thing. Now we've talked about why you batch at all. You paid for one read of the weights, so you may as well fill it. And I left a question hanging back then. Does batching help every part of a step equally? It doesn't. So we pick that up first, and then we go through when your server is actually allowed to redraw the batch. I'm Mani Khanuja, and I'm a Principal Generative AI Specialist Solutions Architect at AWS. Let's get into it. So, two things about batching that usually go unsaid, and both of them matter today. So here's the first one, right? Attention doesn't have any weights of its own. And I want to be careful with that because there are weights all around it. Your queries and your keys and your values are produced by a projection, and that projection does get shared across your whole batch. But the attention step itself has no parameters in it at all. A token just looks back over its own history and works out what to pay attention to. So what does batching buy you there? No weight reuse. And everywhere else, reusing the weights is the entire point of batching. One read of that projection serves every request in your batch, and attention has no weights to read at all. So each request just works through its own history on its own. And the Orca paper says as much. There's no benefit to reusing model parameters because this operation doesn't have any. Keep that one because it's the reason the fix we're getting to costs almost nothing. And the other thing is your ceiling. So how big can a batch get? Not as big as you'd like. Every request you admit brings its own KV cache along with it, and we did that formula earlier in the course, and it grows every single time the conversation gets longer. So your real batch size is set by how much KV cache you can actually hold. And the number in your config, that's only the ceiling you asked for. And what does getting near that ceiling buy you? So I ran this on one NVIDIA L4 with an 8 billion parameter model on it. One request at a time, the whole server puts out about 16 tokens a second. 32 at a time, that same server puts out about 382. So that's everybody's tokens added up together, and it's 23 times as many off the very same card. And what happened to one individual person sitting in there while the server was doing all of that? Their gap between tokens went from 60 milliseconds to 79. So now the part that was wrong for years, and it's worth going slowly here, because once you can see it, the fix is obvious. Think about a washing machine at a laundrette. You fill it, you start it, and it runs. And nobody's clothes come out until the wash is finished. And you can't put a sock in halfway through either. That's static batching, and it's genuinely how serving used to work, because you gather up a set of requests and you start them all together, and then you release the lot of them when the last one finishes. All of them together. So somebody said, fine, let's build the batch as requests actually turn up, and the server collects arrivals until it has a full batch or until a short timer runs out, and then off it goes. That's dynamic batching. It is better, and every serving stack had it. But look at what didn't change. It still releases that whole batch when the last one finishes. So you still can't put a sock in halfway through. And that's the bug. Both of those make one decision per request. So the server decides who is in right at the start, and then it doesn't get to revisit that until the request is done. Request granularity, and it costs you three things. Your short request finished at step 4, and it is still sitting in that batch at step 400 doing arithmetic nobody will ever read, and everybody else in there is waiting on whoever asked the longest question. And anybody turning up a millisecond after that batch started waits for the entire wash. So how would you know if this is you? Your server can tell you the average batch size it's actually running. And we found that number earlier in the course. So go and look. And if it's near 1 while your queue is full, then you aren't batching at all, whatever your config says. So the fix arrived in a paper called Orca at OSDI in 2022, and there's no RxIV number for that one. So if you go looking for it, look in the USNX proceedings. And it really is one idea. Move that decision from request granularity to iteration granularity. The engine runs exactly one step, produces one token for everybody in it, and hands control straight back to the scheduler. And the scheduler chooses again from nothing. So what changes? Anybody who finished on that step leaves immediately and stops costing you anything. And anybody who arrived while that step was running joins in on the very next one. So your machine now stops between every turn of the drum, and people take their washing out and put theirs in. And how does it choose? It sorts everybody waiting by when they turned up. So first come, first served, and it takes them in that order up to a maximum batch size. Then one more check. And this is the interesting one. Before it lets a new request in, it reserves enough KV cache for the longest answer that request is allowed to give. All of it up front. And if that won't fit, it stops there and takes nobody else this round. So is that a good design? Half of it is. A request can never run out of cache halfway through and get thrown out again. And almost nobody uses their maximum, so you have set aside memory for answers that never get written, and your batch is smaller than it needed to be. So the rest of this module goes after that weakness. And Orca's maximum batch size is sitting in your config today. In vLLM, it's called maxnum SX, and the documentation describes it as the maximum number of sequences to be processed in a single iteration. Single iteration. So that's Orca's number, still there 4 years later. Now there's a problem with all of this, and you might have spotted it already. If one request in your step is reading a long prompt for the first time, and another is producing its single next word, then everybody has a different number of tokens to get through. And a batch mathematically is a rectangle. You stack requests up, and they all have to be the same width. So how do you stack one token next to 300? And Orca's answer is that you don't. You take every token in the step from everybody and you lay them out in one long line. So 7 tokens from 4 requests is just 7 rows. And every operation that works 1 token at a time runs straight down that line without caring whose token is whose. Then at attention you split and you run it separately for each request, because that's the one place where it matters whose history you're reading, and then you merge straight back into the line and carry on. That's it. So what does that split cost you? Almost nothing, and now you know why. You gave up batching on attention, and that was never buying you weight reuse anyway, because there are no weights in there. And everything that does have weights, still batched right across the whole step. And the authors were straight about what it did cost them. Their engine on its own, on a fixed batch, was similar or slightly worse than NVIDIA's FasterTransformer. And that was the fast production server of the day. They gave up a little kernel efficiency, and the scheduler made up the difference. So how much difference are we talking about? Quite a lot, and here are their numbers. They held the latency fixed. Same median latency per generated token, 190 milliseconds on a 175 billion parameter model. At that latency, FasterTransformer served 0.185 requests a second, and Orca served 6.81. So 36.9 times the traffic on the same hardware at the same latency your user feels. And none of that is a faster kernel, right? The math is the same math. They changed how often the scheduler gets to change its mind. So where has it ended up? Well, NVIDIA stopped developing FasterTransformer and sent everybody to tensorrt-llm instead. And tensorrt-llm does iteration-level batching. They call it in-flight batching, and their own docs say that's the same thing the rest of us call continuous batching. And vLLM took it further. In their current engine, there is no prefill and no decode as far as the scheduler is concerned. It treats your prompt tokens and its own output tokens the same way, and a scheduling decision is one dictionary, request ID, and a number of tokens. That's the whole thing, and I read it in version 0.27.1, and that's current as I record this. And because it's that simple, the same representation carries chunked prefill and prefix caching and speculative decoding, and we get to all 3 of those later in this course. And there is one part of this that people still argue about. Everybody redecides every step now, so the granularity is settled, and which request you pick is very much not. So look at sglang, and that's another open source serving engine doing the same job as vLLM. It used to pick whoever's prompt started off the same way as something it had already worked on, because then the cache was already warm for them. And today it just goes first come, first served. Now there's a bill for all of this, and it turns up in a flag a lot of people set without knowing what it does. We met CUDA graphs earlier in the course when we were setting up the profiler. So what is one? You capture a sequence of GPU jobs once, and then you replay the whole lot as a single submission. So why would you want that here? Because a decode step is tiny. It's a long chain of small jobs, and before your GPU can run any one of them, your CPU has to set up its arguments and hand it over. And when the job itself takes a few microseconds, that handing over is a real share of your time. PyTorch's own documentation is blunt about what a replay saves you. It skips every layer of argument setup and dispatch, and the whole thing goes over as a single call. So graphs help your decode a lot more than your prefill. And they help a small batch more than a big one, because a big prefill step already has enough real work in it to hide that setup cost. But now put that next to everything we just said. Every step is a different shape now, and there might be 5 requests in this one and 9 in the next. And PyTorch is just as blunt on that side, and these are their words. Dynamic shapes are prohibited. So a captured graph assumes every tensor is exactly the same size on every single replay. And if your batch keeps changing size on it, that graph is no use to you. So how do you get both? You capture a set of sizes and round up to the nearest one. vLLM captures 1, 2, 4, then every 8 up to 256. So 5 requests in your step will run the graph that was built for 8, and 3 of those places are padding. And that is the cost of getting both things at once. Compute you paid for and threw away, plus the memory to hold all those captured graphs. And the flag is -- enforce eager, and it turns that capture off, and it turns torch compile off along with it, and vLLM will tell you so in your log. So when do you want enforce eager on? When you're debugging or profiling, or when you want the server up quickly and you're short of memory? And what should you not do with it? Don't leave it on and then wonder why your decode is slower than the blog post promised. And don't treat turning it off as a guaranteed win either, because how much that capture buys you depends on your batch sizes and your backend. So measure your own decode both ways. What actually changed here? Nobody made the math faster, right? They just changed how often the server is allowed to change its mind. And every number in this episode comes from that. And that is your washing machine stopping between every turn of the drum. Ridiculous for laundry, right? And it is exactly right for a GPU, because your requests turn up at different times and they finish at different times, and they were never once going to be ready together. They never are. So what would I like you to go and do this week? 2 things, and neither takes long. Find the average batch size your server is actually running and put it next to the number you assumed. And if those two disagree, something in front of your engine is still building batches the old way, and that is worth an afternoon. And the other one, find your maximum batch size in your config, work out what your KV cache can genuinely hold, and see which of the two is stopping you. Because if it's the config, that's a one-line change. And if it's the cache, no config change is going to save you, and you've got a different problem. So which one was it for you? Tell me in the comments, because I would like to know how many people are quietly running with a batch of 1. So that was iteration level scheduling. The rest of the course is in the playlist in order, and I'll see you in there.